Okay, so we all know that large language models are, well, incredible. They can write code, they can whip up a sonnet, they can even help scientists discover new drugs. But if you ask how they actually do any of that, things get a little quiet. It's like, we know they work, but what is really going on inside that massive digital brain? Well, I've been digging into some really fascinating research that suggests the answer might be hiding in a place you would absolutely never, ever think to look.
I know. I know that sounds completely out there, right? Like something from a sci-fi movie. But just for a second, what if that incredibly complex billion-parameter dance happening inside a model like GPT-2 could be explained by the same basic physics that makes a compass point north? It's a truly wild idea, but you've got to stick with me on this, because when researchers actually tested it, the results were, frankly, kind of shocking.
And really, this is the fundamental problem we're facing in AI right now. We've built these unbelievably powerful tools, but we don't fully understand their internal logic. It's what we call the black box problem. You put a question in, you get an answer out, but that whole process in the middle, it's a mystery. And that makes them really hard to trust, impossible to debug when they go wrong, and difficult to truly control.
So to try and crack open that black box, a new approach is borrowing a lens from a totally different world, condensed matter physics. And this is where we get the central idea for this whole thing, the spin bath analogy.
Okay, so what on earth is a spin bath analogy? Well, the core idea is that the attention mechanism, the part of the AI that decides which words in a sentence are important for understanding the context, can actually be described mathematically as a system of tiny interacting magnets, or spins. Just try to picture every word or token in a sentence as its own little magnet, with its own north and south pole.
And this image right here just makes it so clear. On the left, you've got pure physics, a single spin sort of wobbling or precessing around an invisible magnetic field. Now look to the right. That's the AI. You've got a single token, and its state is being pulled and twisted around by the context vector, which is just the combined influence of all the other words around it. The mind-blowing part? The math that describes both of these processes is almost identical.
Let's break that down even more, because this is the key. In your magnetic system, you have spins. In the language model, the equivalent is token embeddings. That's just the fancy term for the string of numbers that represents a word. The force that connects two spins in physics is the exchange coupling. In the AI, that's the query key matrix, which calculates how much any two words should influence each other. And finally, the total energy of the whole magnet system, that maps directly to the AI's attention score, which tells it what to focus on. It's basically a direct translation.
So this is a beautiful, elegant theory, right? But the big question is, does it actually hold up in the real world? To find out, researchers decided to test it on a real, live model, GPT-2. And they weren't just tinkering here. They were diving right into the belly of the beast to see if this crazy magnet idea had any legs. Now, to do this kind of test, you need a really precise measuring stick. And for this experiment, that stick is called the logit difference. It sounds complicated, but it's actually super simple. It's just a number that tells you exactly how much more the AI wants to say, for example, Berlin instead of Rome as the next word in a sentence. It gives us a hard number for the AI's preference, something we can actually compare our physics theory against.
And the experiment itself was incredibly rigorous. First, they made a simple data set of facts, things like the capital of Germany is. Then they went inside GPT-2 and pulled out the raw data, those exchange couplings, from all 144 of its attention heads. Then came the big comparison. They used their simple physics model to predict the logit difference, and then they checked to see what the actual GPT-2 did. The goal was to see if the prediction matched reality.
And this, of course, is the million-dollar question. Could this incredibly simple model, borrowed from the physics of magnets, actually predict the behavior of this massively complex, multi-billion parameter AI?
Well, the answer turned out to be a massive yes, but it came with a twist that absolutely no one saw coming. The theory worked perfectly for one specific component, just not in the way you'd think.
Okay, so here it is. For one specific little component in the AI's brain, they called it Layer 3, Head 5, the predictions from the physics model were almost perfectly correlated with what the AI did. But look at that chart. See how the red line is sloping down? That means it was a negative correlation. In other words, the more the physics model predicted this head would choose the right answer, the more it actually chose the wrong one. It's absolutely nuts.
Let's just sit with that for a second, because it's wild. It means that while the rest of the GPT-2 model was working to find the right answer, this one little part was actively, consistently fighting against it. They found a tiny saboteur inside the machine. They called it the antagonist head.
And this amazing visual shows us exactly how it was being antagonistic. Think of this as the head's internal preference map. The black arrow is the context pointing toward the right answer. But that big red area, that's where this head wants to go. And what's sitting right in the heart of that red zone? The wrong answer, Rome. The correct answer, Berlin, is way over in the blue. This head is literally wired to prefer the incorrect choice.
So, the obvious solution is to just get rid of the bad part, right? Just perform a little digital brain surgery. Well, it's not that simple. When they actually turned off the antagonist head, it barely changed the final answer. But then, when they turned off a different, seemingly random head, the model's wrong answer got even worse. It just goes to show you, the AI's final decision isn't about one hero or one villain. It's more like a chaotic committee meeting where all these different parts are arguing and the final decision just emerges. Okay, so being able to find these weird antagonist heads is huge for understanding the AIs we already have. But what if we can flip this idea around? This discovery isn't just about interpretation. It might actually give us a blueprint for building entirely new kinds of AI, using the principles of physics from the very beginning.
So let's look at how this might work. On the left is how a lot of generative models work now. Think of it like a random walk, starting with a bunch of noise and using a black box network to hopefully guide it somewhere useful. On the right is this new spin diffusion idea. It's not a random walk, it's a guided orbit. The force pushing it along isn't some mysterious network, it's a well-understood physics equation. It's structured, it's predictable.
And here's the basic recipe. First, you start with a clean spin representing a word, and you mess it up with noise. Simple enough. Second, you train a network to learn how to undo that mess. But here's the absolute key, step 3. To generate something new, you don't just use the network. You use both the network and the actual laws of physics to steer that noisy spin back to a clear, coherent answer. It's this incredible partnership between learned intuition and fundamental physical principles.
I just love how the researchers put it here. This whole approach changes the game. You're replacing a black box drifter, this mysterious process that we hope works, with something that has a rich, understandable, and geometrically solid structure baked right into its DNA. You're swapping chaos for order. So when you zoom out, what does this all really mean for the future? Well, it feels like we're watching the construction of a powerful new bridge, one that connects the statistical, data-driven world of AI with the fundamental, principled world of physics.
All right, so if you're going to take away just a few things from all this, let it be these. First, the incredibly complex attention mechanism inside these models can be understood as a simple system of tiny magnets. Second, using that lens, we can actually pinpoint the jobs of individual components, even the really weird ones like antagonist heads. And most importantly, this isn't just about looking backward. It gives us a brand new blueprint for building the next generation of AI based on the solid ground of physics.
And that really brings us back to that huge kind of crazy question from the start. Could this simple physics that governs a magnet really be the key to unlocking the future of AI? You know, by looking at the mind of the machine through this new lens, we haven't just found a new way to interpret AI, we might have just stumbled upon a brand new way to build it from the ground up. That black box, well, it's starting to look just a little bit more transparent.